Alright, so you've already looked at the basic form of a exponential function. You know where to locate your base, you know where to locate your original value, your asymptote. Now we're going to actually look at how to write some of these equations and what they actually mean. So if you read your problem, since January of 1980, the population of the city of Brownville has grown according to the mathematical model y equals 720,500 times 1.022 to the x power, where x is the number of years since January 1980. So explain what 720,500 is and what 1.022 represent. So this is pretty easy stuff. Since we're talking about population, that's a number of people. The 720,500 is your original. That's your original population. Okay, this is your number of people. Alright, the 1.022, it represents the fact that your population is growing. Okay, so 1.022 represents growth. Alright, and it actually means that you are growing by a certain amount. If you take 1 away from the 1.022, you would get 0.022. And if you move that decimal place twice, you would see that that is 2.2%. That's what that 1.022 means. It means you're growing by 2.2% every single year. So in this next problem, what would be the population in the year 2000 if it continues at the same rate? Well, you would just use the formula that you're given, and you would just plug in the fact that in the year 2000, since we're talking about since 1980, that has been 20 years. So if I plug that in, 720,500, 1.022 to the 20th power is 0.75. So what I'm going to do is, since we're talking about a number of people, I'm going to round that up to 2. Right? So that is 1,113,402 people. Okay? That's your new population. Alright, use this model to predict when the population will first reach 1 million. Well, we know it happened before 20 years, since we know that our population at 20 years is over 1 million. So what I would do is, here's where your calculator's table would come in handy. Okay, you'd type that function into the calculator with x being the exponent, so it actually changes the population every single year. And you should notice that here in year 15, that's 998,613. The next year it says 1.020583 times 10 to the 6th. Okay, that just means that you move that decimal over 6 spots. So it would move from there, 1, 2, 3, 4, 5, 6, which is now over 1 million. So that answer would be about 16 years. Alright, so here's another example. A population of 800 beetles is growing each month at a rate of 5%. Okay, write an equation to represent this thing. Okay, represent the number of beetles at time x. Well, if you have 800 beetles, okay, and they're growing exponentially by 5%, okay, I like to do this. You have 100%, you are adding 5% each year, which puts you at 105%. Okay, that as a decimal is 1.05. So there's your base. Alright, and since it's happening every single month, okay, that's exponential growth, and our exponent is just an x. So now how many would there be in 8 months? I would just pull up my calculator, and I would type in that formula with x being an 8. And that gives me, again, I'm going to round this since we're talking about a population, about 1,182 beetles. Alright, so One of the best applications of exponential decay is a half-life, okay, specifically with medicines. And so in this problem, the half-life of Advil is being discussed. And half-life, you can imagine, has the base of 0.5. And in this equation, the R stands for how much of the drug is still in your body, the M stands for how much you originally took, and T is the amount of hours that have passed. Okay? So in this problem, it says that a 200 milligram dosage is taken at 1. How many milligrams of the medication will remain at 6?
Good afternoon. We have one.
Sorry about that. So, you would start off with, you have 200. You have the fact that you're multiplying by 0.5. And since from 1 to 6, that would be 5 hours. And that's 5 over 2. Okay, so you just type that in the calculator, and you would get all right, 35.35. So you have about 35.35 milligrams in your system still. Okay. This next question is still asking about the same scenario. The only thing that's changed is it says 12 hours later instead of 5 hours later. So you would just change that to 12 over 2. All right. So that would be 3.125 milligrams. Okay? So even 12 hours after you took a medication, you still have some of the drug in your system. Eventually, it basically runs out, but because of that asymptote being at 0, it truly never will completely be out of your system. You will always have some trace of that drug. Now, it might not show up on a test, but it's still there. Alright, and so then this last problem, one more example. Your new computer costs $1,500, but it depreciates, so I can imagine that you might be able to figure out what that means. That means it decreases in value by 18% each year. Okay, so that means that you are taking away 18% each year, which means that you actually still have 82% of the cost, or of its value. So your equation would be something like this. You have $1,500 value, 82% of it stays every single year. So that's to the x power. That's an exponential. Now you just figure this out. How much will it be worth in 6 years? Alright, in 6 years, that's 1,500.82 to the 6th power, and that's right at $456. Alright. Now the final question about how long will it take for your computer is worth close to $0. Okay, so this was really aggravating. I had to put it into a table. I just used my formula. And then I started scrolling. Okay, I knew it was going to be a while before it was actually close to 0. So this is, 0.04 means this is 4 cents, 3 cents, works its way down to a cent. So really technically that's $0. But if you are technically trying to get 0.00, the first time that actually happens is after 61 years. Okay, so 61 years until it's $0. Alright, so that's a long time. So anyway, hopefully this helps. Go back through, watch something again if you had any questions. But hopefully this will help you get your work done.